Okay, so I'm going to look now at how to represent a graph. And you've seen a bit of this already. So a typical way of representing a graph is with some points, perhaps 4 points, maybe throw in a loop or two. So this is an example of a graph. And another way of representing the graph is by listing every pair that makes an edge. So I can list the edges. In this case, there is an edge between A and B. Now I'm going to note that there's a little discrepancy between how edges are described and the figures sometimes. So it is common in many sources that edges are always listed as a pair with parentheses. But we've learned that this notation is supposed to refer to order. So when there are parentheses, it's supposed to mean that one of them is the starting point and one of them is the ending point, and that's not the situation here. So what we are going to do is not use parentheses, but curly brackets. So there is an edge between A and B, and there's no arrow here, so curly brackets. There's an edge between B and itself, a loop. Also A to C, A to D, and C to D. So a graph as a figure and a graph as a list of edges. And a third way is called the adjacency matrix. And there are other ways as well, but I'm just focusing on these three. So in an adjacency matrix, we take our graph and we want to write it as a matrix where we have one row for each vertex and one column for each vertex. And then if there is an edge, say from A to A, I would put a 1 here. Well, looking at our graph, there is not an edge between A and A, so I put a 0. If there is an edge from A to B, I would put a 1 there, and there is one. From A to C, I would put a 1, and then from A to D. And then looking at the second row, if there is an edge from B to A, a 1 will go there. From B to B, a 1 would go there. An edge from B to C would result in a 1. But looking back here, there is no edge between B and C. So I get a 0. And you continue in this fashion. So C to A had an edge, and C to D, and then D to A had an edge, and D to C. So this adjacency matrix represents that graph as well. And as I said, there are other methods. You can find things like adjacency list. Is another way of representing graphs, but these are the three that we'll focus on. Now, I don't have to necessarily go from a graph to a matrix. I could also go the other way around. If you were given the matrix, I could say, draw the graph for the following matrix. So I'll give a matrix here. Let's say our adjacency matrix is following. It'll take a minute to write out all the entries. Okay, so I have this graph and I want to, or this matrix, and I want to write the corresponding graph. I did not label the rows and columns here. because the labels on a graph aren't actually important. We'll discuss that later with isomorphism, but it might be helpful to stick some labels in just for our own purposes. Now, I don't know what the figure is going to look like, so I'm just going to draw the points in a cycle. It might be that there's a nicer way of doing this, but if I don't know beforehand what the figure is going to look like, this is a decent option. So now I'll go across that first row. There's an edge between A and A to E. So A to A is that loop, and A to E is here. Then the second row, there's an edge from B to C and E. So B to C and B to E. Then there's an edge from C to B and C and D. So C goes to B, C, D. I already have B, then C, and then D. Now look at row D. It only has an edge to C, and I've already drawn that. Now E has A and B, and I've already drawn those. So I'm done. This graph and that adjacency matrix represent the same figure. Now, it is possible to do an adjacency matrix when you have multiple edges. If I had, let's say, 2 edges between A and E, I might put a 2 there and a 2 here. And that would mean I have 2 edges between those. So a 1 means 1 edge, a 2 means 2 edges, and so on.